we'll be discussing dynamic equilibrium and the solubility of three types of solutions: at saturation, unsaturated, and supersaturated. Dynamic equilibrium is when the forward reaction and the reverse reaction is occurring at the same rate. Although there are no macroscopic, no visible changes, there is a continuous change on a molecular level, which is why it's called dynamic. The specific type of equilibrium discussed in this video is solubility equilibrium. As we know, the molecules are constantly in motion. In terms of solubility, molecules are continuously dissolving and solidifying. As a result, solubility equilibrium is achieved when the rate of crystallization is equal to the rate of dissolution. In other words, when the rate of these particles leaving the solid and the rate at which they are returning to the solid is the same, it is at equilibrium. A saturated solution is a solution that contains the maximum amount of solute that can be dissolved under a specific condition, a specific temperature and pressure. What is happening on a molecular level in a saturated solution? This will be explained through the combination of iron 2 nitrate and ammonium hydroxide. The chemical equation of these solutions is shown here. Once a salt, or otherwise known as an ionic substance, is dissolved in water, they will separate into ions, as you can see. These solutions are known as aqueous, commonly denoted as AQ, which you can observe here. When two aqueous solutions are mixed together, the different ions are combined in a limited volume. Occasionally, the amount of a certain substance that can be dissolved, the saturation point, has been passed, and the result is a solid known as precipitate. All salts have different solubility points and saturation points under a consistent condition. These lines here shows the saturation points of various solutions as the temperature increases. The precipitate that forms in a solution is the compound that has a lower solubility than other products. It will surpass the saturation point before the other products in the solution, which is why they bond together and leave the solution. The trial ion product Q is a test calculation using measured concentration values of a system in the equilibrium expression to see how it compares to the solubility product constant Ksp. Given this equation, Q is equal to the concentration of the product raised to its respective constant divided by the concentration of the reactant raised to its respective constant. The equation to solve for Q and Ksp, as you can see, is the same. The only difference is that the solubility product constant is limited to the concentration when the solution is at equilibrium. If Q is equal to Ksp, then it means the solution is at saturation, and it will not produce a precipitate. It is only when the trial ion product is greater than the solubility product constant and that a precipitate will form. Back to our example. The Ksp value of iron 2 hydroxide is given to be as 4.9 times 10 to the negative 17, and the dissociation equation is shown here. To find the concentration of which iron 2 hydroxide is at saturation, we can plug the dissociation equation into the solubility equilibrium law. Because the reactant is a solid and the concentration of a solid cannot change, it can be removed from the equation and just be considered as part of the solubility product constant. By substituting in x, we can solve for the solubility of iron 2 hydroxide, which in this case is 2.3 times 10 to the negative 6 moles per liter. Because the iron ion has a 1-to-1 ratio with iron 2 hydroxide, as seen in the dissociation equation, the solubility of iron 2 hydroxide is also 2.3 times 10 to the negative 6 moles per liter. By working backwards and plugging in the concentration to this equation, you can find the Q values, which then can be compared to the Ksp. When Q is equal to Ksp, the solution is at saturation. This method of calculation can also be applied to unsaturated and supersaturated solutions.
An unsaturated solution is when there is too little solute in the solvent to allow the solution to form precipitate or crystals. That is because the amount of salt that you add is still dissolvable. For example, if you add NaCl2 to water, the salt seems to disappear. NaCl2 salt breaks into Na ions and Cl ions inside the solution. At the same point, there will be too much ions in the solution. Therefore, some ions collide together to form NaCl2 again, but in small amounts that does not appear as precipitate. If you want to know if the solution will form a precipitate or not, given the amount that you want to add can be calculated using KSP and Q. By calculating KSP value and Q value and comparing them, there will be no precipitate formation only if the Q value is smaller than the KSP value.
Okay, go.
Common ion effect is the reduction of solubility of a salt caused by the presence of another salt having common ion. The effect of a common ion on the solubility of a substance is that if you have a saturated solution of a solute and you add a common ion, then the solute will precipitate out, meaning its solubility has been reduced. If you have a diluted, unsaturated solution, then a common ion will have no effect. Moreover, the effect will be decreasing the solubility, which decreases the ionization, so that the reaction will occur in reverse. They shift the equilibrium as a result of increased concentration in aqueous ions to precipitate out of the solution. For instance, in this solution, if more ions of lead or iodate were added to the solution, then crystals of lead iodate would form. How does this happen? This is the result of a common ion effect, a result of addition ions increasing the concentration allow for precipitate to go out of the solution. This shows how the lowering of the solubility of ionic compounds by the addition of a common ion leads to the common ion effect occurring.
A supersaturated solution is when a solution becomes unstable. This results in a tendency for the extra solute found within the solution to precipitate, indicating that the solution whose concentration of solute exceeds the equilibrium constant within the solution. The result for the solution becoming unstable is because entropy occurs within the solution itself, which allows for the precipitate to become spontaneous. When a solid is dissolved, there is a fast-forward reaction, a dissolving process, then the reverse reaction, and then finally comes the crystallization process. If you want to look at this in a different way, you can look at it in the sense of vapor. Now, in vapor, you can compare by looking at the vapor of a compound that has a high partial pressure compared to the vapor pressure of that compound itself. Now, we're going to look at an equation to determine a question that many people ask. What is happening on the molecular level in a supersaturated solution? This will be explained through the combination of aqueous form silver nitrate and aqueous form sodium chromate. Now, as you can see in this equation, the solid is obviously going to be the silver chromate. Solids are present in supersaturated solutions. The solid precipitates out of the solution to try to maintain equilibrium. When the solution reaches equilibrium in a supersaturated solution, it surpasses the dynamic equilibrium for precipitate to leave the solution. The reasoning behind this is because the rates of crystallization and dissolution aren't equal. After they exceed equilibrium, which allows the rate of crystallization to increase and the rate of dissolution to decrease. Now, when two solutions are mixed together with one another, including silver nitrate and sodium chromate, this allows for the precipitate to become spontaneous as a result of entropy, and this precipitate is formed from the solid. After crystallization, the solution will change so that it can return back to dynamic equilibrium. Once crystallization occurs, it affects its surrounding environment and then the solution. The reason for this is explained through dynamic equilibrium. Once crystallization occurs, this allows for a great amount of ions found in the little amount of solution. The ions bond together and precipitate out of the solution. The solubility of a solid is very low compared to the other products, which is why generally solids precipitate out of the solution. This is how supersaturated solutions occur and work. Now, looking at the equation above, we're going to go into the dissociation equation of silver chromate. As you can see in this one, we know that the solid is obviously going to be silver chromate for the reason that it's the least soluble salt.
Q is the ion product, and Q is the ion product, and through the ion product, it is determined through mathematical equations the relationship with KSP, which indicates if the precipitate will occur or not. In this case of a supersaturated solution, it will only occur if Q is greater than KSP. So now, when we're looking at this, we can look at it in a different way. So what we can do is determine through it mathematically. As mentioned before, the first thing we have to do is determine the equilibrium solubility. Through this, we know that the solid is not going to be part of the solution for the reason that is already incorporated within KSP, meaning we can easily just take it out and be left with this. Now, what can be used is the Q value. The Q value can be used to determine this. Since we know that the KSP value is the same as the Q value, that means that the same formula can be used. When determining the Q value, you can use the values of X and determine the concentrations of C, D, A, and B. Once you figure out Q, Q must be greater than KSP in order for a precipitate to occur. In this case, always remember that a precipitate can only occur if Q is greater than KSP. This can be figured out mathematically and experimentally. Occasionally, in a supersaturated solution, the precipitate needs activation energy so that it's able to precipitate out of the solution. However, this does not usually occur because majority of the time a precipitate can occur with no problems. In some cases, there are activation energy barriers that don't allow for a precipitate to form on its own. In this case, a certain amount of energy is needed to surpass the activation energy content so that the precipitate can occur and be produced. As a result, the precipitate can only occur after overcoming an activation energy barrier. This barrier can be looked at through this analogy right here. Now, when we look at this man, he's trying to get from point A to point B, but the only way he'll get there is through amount of strength, or we can say an amount of activation energy to surpass the hill so that it can pass through. Now, we can look at this through solubility. In the sense of, through solubility, it can be looked at as the reactants, which are going to be our dissolved ions, needing a certain amount of activation energy to be able to produce the products, which is a solid, or as many people would say, is a precipitate. Supersaturated solutions are usually unstable, but can become stable when an activation energy barrier is surmounted, and the precipitate can occur with no other problems. These barriers result from the nucleation processes and activated complex formations. For many who may not know, nucleation processes is extremely restricted potential of distinct phases. This is a process needed to make sugar candy, gaseous bubbles, crystals, or glassy regions. So, just to put it in simpler words, it is the physical reaction which occurs when components of a solution precipitate out of the solution. Moreover, different quantities of activation energy are needed in different precipitates, and also, temperature further determines the quantity of an activation energy needed to surpass the barrier. This process of crystallization is an exothermic reaction, as was seen in this picture. It starts very high and ends very low, and in this way it releases energy, it gives off heat into its surroundings. Now, you may think, how are supersaturated solutions needed in our everyday lives? They are needed in our everyday lives because they provide us a benefit for creating sugar cookery and interesting structures with water. Sugar cookery can be produced through these supersaturated solutions to make carbonated water, water soda, rock candy, sugar candy, and etc. Moreover, a supersaturated solution from sodium